Video 22 of the master course Quantum Chemistry of Molecular Electromagnetic Properties. The topic of this lecture is transition probabilities and rates. In order to get a better understanding of our time-dependent wave function as we have derived them in the last lecture, and in particular of the first order correction to the wave function, we will do exactly the same as we have done in the chapter on time-independent perturbation theory. We will expand our first order correction to the time-dependent wave function in a complete set of unperturbed wave functions, which of course we assume that we know. However, there are two differences here. One difference is because we are now in the time-dependent case, and therefore also our expansion coefficients are going to be time-dependent, and we will use also basis functions, which are now time-dependent. These basis functions are then just the time-dependent unperturbed wave function, which means our normal unperturbed wave functions multiplied with this time-dependent phase factor, so the phase factor which carries the time dependence. And again, like in the unperturbed perturbation theory, in order to get the coefficients, we project this expansion, meaning project the first order wave function, against one of the basis functions. And the basis functions here are these time-dependent basis functions, so we have to project against, in order to get the coefficients n, we have to project against not only the unperturbed wave function psi n zeroth order, but psi n zeroth order multiplied with this time-dependent phase factor. Now the norm of our expansion coefficients then, like in the case of time-independent perturbation theory, what the probability is to find the system in the stationary state psi n, and here then psi n at the time t. Now the derivation of time-dependent perturbation theory in the last lecture, we assumed that the system was in the state psi 0, the unperturbed state psi 0, before the perturbation was turned on. And you can easily see that because in the expansion of the time-dependent wave function, the zeroth order function was this psi 0. And therefore, these expansion coefficients here for the first order correction to the wave function, we can then interpret as the probability for the transition from the original state psi 0 to this state psi n now. So it's what is called a transition probability. Now in the rest of this lecture we will now derive an expression for these transition probabilities and try to understand what it is. So let's now insert the expression for the first order correction to the time-dependent wave function, which we had derived in the last lecture, here in our expression for the coefficients. So that's what I have done here. Here I have my basis function, and that is my first order correction to the wave function. Now the first thing, of course, we can see these two exponentials cancel each other. The product of those is 1, so they go away. And then I can move, of course, the integral over t prime now outside of my integral here, because the Dirac notation integral is, of course, an integral over positions and maybe spin of electrons, whereas this is an integral over time, so I can interchange them. And then what I also have done in going from the first line to the second line is I have, please note, this is the perturbation Hamiltonian in the interaction picture or a Dirac representation. And here I have written it explicitly out. Now, the unperturbed wave functions psi 0 and psi n here in the ket and here in the bra, they are the eigenfunction of our unperturbed Hamiltonian, and therefore I can let the exponential operator here act on this wave function, which means that the unperturbed Hamiltonian is then replaced by the corresponding eigenvalue of this Hamiltonian with this wave function, which is a0 zeroth order, and this place here it's En, the energy of the end state, zeroth order energy of the end states En. And then the exponentials are no longer operators, but they're just numbers. So I can move them together. And of course, I can also move them out of the integral over positions of the electrons. And if I then combine them, here we have a minus sign and here a plus sign. So we'll get En 0th order minus E0 0th order, and I have H divided by H. And if I call this omega 0n, which is the transition angular frequency, the frequency corresponding to the energy difference, or angular frequency corresponding to the energy difference between my ground state, E0, and my excited state, psi n. So if I introduce this angular frequency, then I get this exponential here, where I here have the energy difference divided by h bar. And I end up with this expression here, where I just have an integral over time here. Here is the exponential. And then I have a more or less normal integral from the ground state to an excited state n with our normal Schrödinger picture perturbation Hamiltonian, which however is time dependent. Now the next step is now to insert this Hamiltonian here, and I will again use the expression which we had in the last lectures. So I will write the Hamiltonian as a product of an operator depending only on positions or canonical momenta of the electrons times the component of the field, which is a time-dependent field, which I again will write with the two exponentials. And that we had here at the end. So I've already combined all the exponentials, what I have done here. So I have the product of this perturbation operator, the operator which only depends on the electrons, and my field, which is everything here, my time-dependent field. Well, here I've written up for electromagnetic field radiation, which can have all frequencies. Therefore, I have an integral here from 0 to infinity over all possible frequencies. And here's the amplitude of the wave with this frequency. And then I have two terms, one with the exponential with minus omega t prime and plus omega t prime, which is the rewriting cosinus omega t in terms of making use of Euler's relation in terms of the two exponentials, which I have combined here. Therefore, I also have this term with the omega n0, the transition frequency, combined with this exponential term and these terms here. And here's the one for minus omega t or minus t prime, and here for plus omega t prime. Now carrying out this integration, the integration over this exponential, which you can either look up in tables or use any mathematical program to get them, I'll get these two expressions. Well, this comes from the first integral, and that one comes from the second integral. Now, if you look at that in the denominator, in both denominators, I have a difference between the transition frequency, which is the energy difference between the two states divided by h bar, and the frequency of our radiation. But I also have the same difference between the frequency up here and the exponential. As a consequence of this, this term is very close to 0 unless the frequency of the radiation is more or less the same as the transition frequency. And similar here, but here the frequency of the radiation has to be equals to minus the transition frequency. In all other cases, meaning for all other frequencies, both of these terms are very small, negligible, which means that our coefficient is basically 0, which means there is no transition from the ground state to the state n, which essentially is Bohr's frequency condition, that in order to have a transition from one state to another state, the frequency of the radiation has to be equal to the energy difference between these two states divided by h bar. Now in the first term, the frequency of the radiation has to be equal to the energy difference. And that means that the first term actually corresponds to absorption of a photon of this energy, Whereas in the second term, the frequency of the radiation had to be equal to minus the transition frequency. So the second term actually corresponds to emission of a photon. And since in a system we can't have at the same time both, we can consider the two processes and therefore the two terms separately. And in the following, we will only look at the absorption then. The transition probability for the norm squared of this term here, which is the norm squared of the expansion coefficient, is then given like this, where this is the result of taking the square. And as I just had discussed, this term here has a sharp maximum at the frequency of the radiation being equal to the transition frequency. So, and that dominates obviously this integral over all the frequencies. And therefore I can approximate this integral by replacing here the amplitude for all the different frequencies just by the value of the amplitude for the only frequency which really matters in the integral, which is the transition frequency. And then I can take it out of the integral because then it's a constant, and I can integrate this term over sinus squared divided by the difference of the two frequencies squared. That's a standard integral again. And so I finally arrive at this expression here, where this is basically the result of the integration, at least pi times t. And then I have here the square of the amplitude of my radiation, of the electric field of the radiation. And I have here actually the same kind of integral as we had in time-independent perturbation theory in the numerator of this sum over states expression for the second order energy correction. Another thing we can note here is that our transition probability depends linear on time, which means it increases linear with time. The rate for the transition from the ground state to the excited state is then of course just the time derivative of the transition probability written here. And if I take the derivative with respect to time t, then of course t disappears and I'm left with the rest of or my transition probability, which is now of course time independent because the transition probability was only linear in time. And this integral, which I already mentioned before, the integral here without taking the norm squared, here I have the norm squared, is called a transition moment. And depending on what kind of operator we have here, if that was, for example, a component of a dipole moment operator, then it would be called the transition dipole moment integral. And we will come back to these integrals or matrix elements when we talk about the calculation of UV spectra, because they are related to the intensity of the transitions.